Hi, my name is Alec Tubbs, and this is my lab report for our fifth and final lab of the semester. The goal of Lab 5 was to compare the results of a physical experiment, dropping a magnet through a roll of tinfoil, with an equivalent experiment created using a computational model in VPython. In both of these situations, the following magnet experiences a force upwards and also induces a current in the tinfoil, so that the magnet actually falls a lot slower than it would if it was just dropped randomly in air and not through the actual tinfoil. The average time calculated for the magnet to fall all the way through the tinfoil in the physical experiment was 0.64 seconds, while the time calculated using the VPython model was only 0.429 seconds. All of the physics concepts at play for this lab deal with magnetism. The first of which is the idea of the magnetic force, which is the force that is actually slowing the magnet down as it falls. The second one is Faraday's law, which states that an induced EMF is equal to the negative change in magnetic flux through a surface. Induced EMF, that's just an extension of Faraday's law. Essentially, if you have a changing magnetic field, it's going to produce some sort of voltage difference. And the last is the idea of Lenz's law, which states that the induced current will essentially try to oppose the changing magnetic field. For the physical experiment, I conducted 5 trials, dropping my bar magnet through the center of the tinfoil roll. I took videos of each trial so that I could then go back later and figure out the timestamps when I dropped the magnet and then the timestamp when the magnet left the tube. In doing this, the numbers when I was scrubbing through the video only went to the tens place, so I had to do a little bit of interpolation to get some more precise results, which you can see in my trials that aren't just 0.6, that are like 0.64 and 0.66. But the average time of my 5 trials was 0.64 seconds. The final and most involved part of the lab was the coding portion, which involved creating a computational model in VPython of the physical experiment we had just carried out. The total length of the code is 200 lines, so I won't go through all of it, but I'll give a basic run through of how the program works and what the results it gives tells us. The first part of the code creates the scene, so to speak. It instantiates the tube object, the magnet object, and initializes variables. The next part of the code involved creating a function to calculate the magnetic field given a magnetic dipole and a distance, which is the same function as we used in a previous lab. I also created a function to calculate the magnetic flux using the formula given in lecture video 43. This function is shown to the right, in the screenshot to the right. The final part of the code involved creating the actual simulation, making a while loop to iteratively calculate the forces on the magnet and update its position accordingly. The tube was modeled as a finite set of rings, and the force on the magnet due to gravity was summed with the force on the magnet due to each individual ring to calculate the total force on the magnet and update its position using concepts from Physics 1. Now I'll answer a few questions about the computational model that were posed in the assignment description. First, what happens to the dynamics of the system when you flip the magnet around? Well, if you flip the magnet around, the magnetic field lines will be pointing the opposite direction because they always point from north to south, but if you flip it around, those are going to go into the opposite direction. So what that's going to cause is that the magnet will experience a force downwards instead of upwards and will actually go through the tube faster. Next, how does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? Well, the average time for the real-world system was 0.64 seconds, and the average time for the computational model was 0.429 seconds. This could be due in part to the fact that when I dropped the magnet through the tube, it could have banged on the sides a little bit, and there could have been another friction force pointing upwards, causing it to fall through slower. I could also improve the computational model by making the sizes of the rings smaller, because in our real world example, we didn't have a bunch of finite rings. It was just a constant sheet of aluminum foil. Lastly, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The velocity versus time plot is shown in the picture to the left, and it is kind of like an exponential decay sort of thing, which leads me to believe that the forces on the magnet aren't necessarily constant, because the velocity versus time plot is not linear. Now to answer some concluding questions. First, what if the resistivity of the conductor were reduced as close to zero as possible? How would the dynamics of the falling magnet change? Well, given the fact that V equals IR, if R goes to zero, then I must be greater. And if I is greater, then the force on the magnet upwards is going to be greater. Next, what if holes or slots were cut into the tube? How would this affect the ring's currents in your model? Well, if there were holes or slits cut into the tube, then the current couldn't make its way all the way around the tube.